I think would be really helpful to put some more meat on the bone, so to speak, for our listeners would be running through maybe one of the classical experiments of quantum mechanics and how the many worlds theory would explain them. I think the double slit experiment is a good place to start, just because that's an easy way to contrast it with, so like Bohmian mechanics, where the wave is guiding the particle. It would be nice to, sum over histories. The experiment is a good way to explain all of them.
Yeah, okay, good. So here's the sort of classic way you do a quantum experiment of this kind. You prepare the system in a two states at once kind of a state, and then you evolve things so that the two possibilities interfere with each other. So let's suppose it's a bit conceptually simpler to do a sort of discrete possible place that the system could be. That the two-slit experiment can be quite fiddly in its details. So imagine I've got a particle, and I can split the particle so it either goes left or right. And then I can bring I've got a left-hand particle beam and a right-hand particle beam. And then I bring the left-hand and right-hand beams back so they cross over each other. And I set things up so if a particle was originally in the left beam, then it'll evolve into a being in the left beam and being in the right beam at the same time. And if I've got a particle in the right beam, likewise it evolves into a being in the left beam and a right beam at the same time. And it's tempting to say, well, that language of being in both beams at the same time must just be picturesque. What you really mean is it's in one beam or the other, but we don't know which one. The problem with that is that we know that if the particle's definitely in the left beam, it could be seen continuing to the left, or it could be seen going right. And we know that if the particle's in the right beam, it could be seen going left, or it could be seen going right. So if it's just that we don't know which beam it's in, our prediction is that we might see it on the left, we might see it on the right. And if we send a whole bunch of particles through the system one at a time, we're going to find a bunch of them end up on the left and a bunch of them end up on the right. That's what you predict if these quantum superpositions are just fancy ways of saying one or other thing is happening. We don't know which. If you set this experiment up right, and it's a delicate game to get it exactly right, but you can organize it so effectively the left-hand beam can cancel out the right-hand beam, and it can do it even if I only send one particle in through at a time. And so you can arrange things so that if the particle can go either left or right, then at the end of the experiment it definitely goes right. Or you could set it up so it definitely goes left. And that's just inexplicable if we just don't know whether the particle went left or it went right. It's only explicable if we want to say that somehow something went left and something went right. So that's a sort of microscopic story about what's going on. And in a certain sense, that's common to pretty much any attempt to solve the measurement problem that's realist. So Bohm's theory, for instance, effectively says something goes left and something goes right. The something, if you like, is an excitation of the quantum wave function or something. In the de Broglie theory, there's, as well as the somethings that go left and some things that go right, there's a something else that, say, only goes left. But it's still crucial that the something is exploring both possibilities. Some physical thing is exploring both possibilities. Then the problem for any account of that kind is to say, well, how do you reconcile that with the fact that we only ever observe one possibility? And so, roughly speaking, dynamical collapse theories change the equations of quantum mechanics so that even though at the microscopic level the system is doing both left and right, when we measure it, somehow the system makes a spontaneous stochastic jump so that only the measuring left occurs and the measuring right is wiped away, or vice versa. And hidden variable theories like Bohm's say, as well as the quantum thing that goes left and right, there's a particle that either goes left or it goes right. And the particles are what the stuff we see in here and are made out of. And the quantum thing that goes left and right at the same time is a weird kind of ghostly thing that is physically important, perhaps, but which is not the kind of thing chairs and tables and cats and dogs are made out of. And Manuel's theory says, yeah, if, it's really true at the macroscopic level that what you measured something on the left and something on the right at the same time. It's just that when you think that through, you'll realize that that corresponds to two separate versions of yourself. So there's a sense in which at the microscopic level, there's not a lot that's very distinctive about the Everettian story. it's only kind of delicately true at most that you can start talking about the world in which the particle went left and the world in which the particle went right. You can kind of get away with that, but it's a little bit metaphorical because you can't understand these worlds as things that go off and do their own separate thing, because they're going to do that interference experiment we talked about. It's that interference experiment that means you have to talk about both things happening at once. And it's that interference experiment that likewise says we can't think about the things happening at once as being in different worlds, at least as long as worlds are thought about as the kind of things that can't interfere with each other and cancel each other out. It's at the macro level where you ask, how is that everything at once story compatible with the fact that we only observe a single definite macro world? That's the point at which the many worlds story and other stories diverge.
And I mean, as far as I can tell, all of the theories that you mentioned and the ones that you didn't, they all have their objections. So the Bohmian mechanics, the pilot wave. What are we supposed to make of this ghostly wave that just continues because the wave doesn't collapse? So they're just out there everywhere.
Yeah, that's right. So there's a philosophical concern about those hidden variable theories, which I've argued for at various points. Yeah. How do we get to say that this thing that is structured for all the world like a classical universe does not indeed represent a classical universe? That's the a priori thing we were talking about earlier. I want to say that a priori, the method by which scientific theories represent things is structural. So there's no real space between the state of the system instantiates something that looks just like classical goings on and saying, well, there are classical goings on. Or if there is some space, it's a kind of parochial space. I mean, you might want to ask, look, is a computer simulation of me as real as me? And there's clearly some sense in which I'm different from the computer simulation, but I'm not sure that difference is any deeper than the fact that champagne definitionally has to be produced in certain regions of France. I mean, so something structurally identical to a bottle of champagne but was made in California is not a bottle of champagne. And sure, you can use language that way sometimes. And if you want to say humans, by definition, are systems instantiated in such and such stuff, but not such and such other stuff, you can say that again. But in terms of the sort of deep questions about what's it physically like to be in those situations, what's the epistemology like, could I know I'm not in those situations, the kind of a priori sort of scientific metaphysics I want is structuralist. And the kind of more philosophically serious defenders of sort of hidden variable theories like Bohm's have a thoroughly non-structuralist conception of the relation between the macro world and our sort of scientific representational tools.
Well, just very quickly, I mean, the only reason I mention the ghost waves, or with some of our histories, the path integral and the contention that a particle really takes all possible paths. The only reason I mention those is that each of these theories has aspects that raise philosophical hackles, and it's not just the many worlds theory, even though that's the one that we're going to be focusing on as we turn to some problems that need to be solved.
That's absolutely right. But let me just strengthen it slightly. I mean, so all of these various approaches have philosophical problems, but at least if we're talking about ways you might change the physics and hold on to scientific realism, I think the most serious problem that the realist alternatives to the many worlds theory have are not philosophical, they're scientific. My real concern with the pilot wave theory, okay, I'm slightly worried about its mysterious empty wave, but what I'm really worried about is the fact that it doesn't have the resources to calculate the magnetic moment of the electron. The theory is just only a very small fragment of our extant science. And so the way I think about Bohm's theory is it's a research project. It's a suggested way we might solve the measurement problem someday. And it's a perfectly intellectually justified, principled task to pursue that research project. I'm not optimistic about its chance of success, but it's serious scientists are doing it. It's worth doing. But it's important not to confuse a research project that might solve the measurement problem someday with a solution to the measurement problem we have in here and now. And a lot of my disagreement with a lot of the advocates of Bohm's theory is they're too, in their public-facing communications, they're a bit too complacent about how large the gap is between the theory we have and the theory we need to have in order to reproduce the predictive success of quantum mechanics.
Mm-hmm. And am I right then that, I mean, one of the major strengths of the many worlds theory is that it doesn't have this problem that Bohmian mechanics has. It can explain, it has the resources to explain the magnetic moment.
Exactly. It's pure interpretation. It's, I mean, perhaps explain could be contentious. It has the resources to predict the magnetic moment of the electron. And as you said yourself earlier, Everett and Bohm are different theories. Everett is an interpretation of the formalism of quantum mechanics, which is the thing we use to calculate the magnetic moment of the electron. Graduate students do. I did this as a grad student. You do the calculation. It's not that I don't know how to explain that, a la Bohm. I just don't know how to do the calculation, at least to the level of making the empirical prediction as to what a measurement device would actually predict.